want us to, just a second, to get into this discussion on the Gibbs-Helmholtz equation. So we have established that G, this is the Gibbs free energy, is given by H minus Ts, where H in this case represents the enthalpy, T is the temperature, and S is entropy. So now when you substitute the value of S from equation E34, now you know E34 was given by S equals to delta G over delta T at constant pressure. So if you put in the value for S, or this expression for S, you get G being equals to H plus T times delta G over delta T at constant P. Now similarly, when you substitute the value of S from equation E22, now equation E22 essentially said that minus S is given by delta A over delta T at constant V. So if you substitute that into this equation for the Helmholtz free energy, we get this expression here. A equals to U plus plus T delta A over delta T at constant V. So those are the two expressions that you get. Now these two equations are regarded as the Gibbs-Helmholtz equation. Other forms of this equation which are most widely used are the ones you're going to get into. So when you consider this reaction, you're moving from reactants to products. Delta G, or the change in the Gibbs free energy, is given by the Gibbs free energy of the products minus the Gibbs free energy of the reactants. So GP here is the sum of the free energies of all the products, and GR is the sum of all the free energies of the reactants. Now from equation E28 is just a reminder. We have seen this one, G equals to H minus TS. There's a way we can express this previous expression here. So GP, or the sum of all the free energies of the products, will be given by HP minus TSP. And for the reactants, GR is given by HR minus TSR. So that now, if you substitute these ones in our previous expression, so we said delta G equals to GP minus GR, you get this expression here. HP minus TSP, so in brackets, minus HR minus TSR. Now, if you open the brackets there and you put the like terms together, this would be equals to, into brackets, HP minus HR minus, of course, here now you're going to have minus TSP minus TSR. So this one you can factor out T and you remain with SP minus SR in brackets. So essentially this one here is delta H and this one is delta S. So delta G is given by delta H minus T delta S. So delta S and delta H, these are, delta S is the entropy change and delta H is enthalpy change of the given isothermal reaction. Okay. So minus delta S here is given as minus SP minus SR. This one can be expressed as delta GP over delta T at constant P minus delta GR over delta T at constant P. Or this expression here can also be expressed as change of, into brackets, GP minus GR over delta T, or with time at constant P. So this one, this, because this here represents delta G, then we can express this as delta G over delta T at constant P. Now when you substitute this result into equation E45, E45 was delta G equals to delta H plus T delta S. So you're putting the expression for delta S here. Then you get delta G equals to delta H plus T times delta G over delta T at constant P. Okay, or this is the change of delta G with temperature at constant pressure. Now, similarly, the same way that we have come up with this expression E47, we can also end up with an expression for delta A, or the change in the Helmholtz free energy. So this would be given by this expression here. Now, by definition, the work function, we know this is the definition for the work function. So from this, delta A equals to delta U minus T delta S. Getting the value of minus delta S from this expression is going to be given by, when you make delta S the subject, or minus delta S the subject of this equation, it's going to be given by delta A minus delta U over T. Now, if you differentiate this first equation here, we get, so dA equals to du, and then for this you have to be differentiating one of the variables, keeping the other constant, and switching to the other one. So this is du minus t ds minus s dt. Now, from the first law of thermodynamics, we know that delta U is given by Q plus W, okay? So from this one, we know that delta U equals to Q minus PDV. PDV here is from work, the definition of W. So from this, dQ equals to du plus PDV, okay? Now at constant volume, dV equals to 0. So if dV equals to 0, then this part of the expression here becomes 0. So that means dQ equals to du. So here, this is what we get here. So for a reversible change, again, for a reversible change, we know that entropy or change in entropy, ds, is given by dq plus dq over t. And from this, we get an expression for dq. That is when you rearrange, when you make dq the subject, dq equals to tds. Okay. So therefore, if here we have said dq equals to du, and here we have said dq equals to tds, then we can say du equals to tds. Okay. So if we take this expression now into our expression for equation 3, which was dA equals to du minus tds minus s dt, but we have already said that du equals to tds. So this one will become tds. So essentially we get dA equals to tds minus s dt. So of course the tds cancel out. We remain with dA being equals to minus s dt. Okay. Now, if you let A1 be the work function in its initial state at temperature T, and A1 plus D A1 be the work function in its initial state at T plus dt. Then let A2 be the work function in the final state at temperature T, and A2 plus dA2 the work function in the final state at T plus dt. Then we can have this. So dA1 is given by minus S1 dt from that expression of dA, and dA2 is given by minus S2 dt. Of course, where S1 and S2 are the entropies of the system in the initial and the final state. So S1 is the initial entropy of the system, and S2 is the final entropy of the system. Now, when you subtract one from the other, so this is the final, and this is the initial. So when you subtract the initial from the final, we get dA2 minus dA1 equals to minus S2 minus S1 dt. Okay, so this essentially can also be expressed as d into brackets change in A is the same as minus change in S dt. Okay, at constant volume, so at constant volume we can say from this expression here we can end up with this expression. When you rearrange it, dt comes to the other side, so d into brackets change in A over dt at constant volume equals to negative change in S. So from this equation here, from equation 2, that was what was it? This equation here, from equation 2, we have this minus change, negative change in S equals to change in A minus change in U over T. Now, on comparing, we have this. So we have here this. This gives us such an expression for minus change in S. Equation 2 also gave us an expression for minus change in S. So that means also this portion would be equals to this portion of the expression. So when you compare the two, we get this change in A minus change in U over T equals to D change in A over dt at constant V. So if you rearrange this expression, then you end up with this change in A equals to change or delta A equals to delta U plus T into brackets D delta change in A over dt at constant V. So here we end up with this expression that is similar to the previous expression that we had found for change in Gibbs free energy. Okay, just go back to it. So this is what we have here. These are the two expressions. So here I was showing you how to arrive at this expression. So these two expressions, they are alternate expressions for the Gibbs-Helmholtz equation. So this another form of the Gibbs-Helmholtz equation is obtained by differentiating delta G over T with respect to time at constant P, as we're going to see below. Just a second. So differentiating delta G over T with respect to time at constant P, this is what we get. So I think we have seen a similar differentiation, essentially for you to see how one arrives at this expression here on the right-hand side. You have to appreciate that delta G over T can be written as T to the power minus 1 delta G. So then from there you can differentiate this with respect to temperature. So with keeping pressure constant. So of course, when you have two variables, first of all, you keep one constant and differentiate the other one, and then swap, keep the other constant and differentiate the first one. So now here, differentiating this, you get this delta G. First of all, differentiate this delta G with respect to temperature. Then keeping pressure constant. Of course, then T was held constant. And then the other one, when you differentiate it, you end up with this expression. So now, of course, you know how you can end up, you can figure out how you can come from this expression to the final expression that we have here. Now, according to E47, this part of the expression here, that is, let's just have a look at this. Okay, E47 was the Gibbs Helmholtz equation that involved the change in Gibbs free energy. You had, if you rearrange that equation, you have this expression being equals to delta G minus delta H. So that means we can substitute it into this expression. Okay, so therefore, if you do that, then that E49 changes becomes change in delta G over T with temperature at constant P equals to delta G minus delta H minus delta G over T squared. So of course, this delta G cancel out. You remain with, it's going to be equals to minus delta H over T squared. Okay, so that is another expression, another form of the Gibbs-Helmholtz equation. So you may be wondering, why are we coming up with all these expression? What is the purpose? So they are very important. These equations are used to calculate the heats of reaction. That is delta H or delta U when delta G and delta A at two temperatures are given. Okay. So for example, we can consider this reaction here, a reaction of hydrogen gas with oxygen to give us water. So the values of enthalpy change and free energy change. So enthalpy change here, we're talking about the delta H and delta G are given. We have delta H being minus 68.32 kilocalories and delta G being minus 56.69 kilocalories. Calculate the value of free energy change at 30 degrees Celsius. So the Gibbs-Helmholtz equation, this one here, gives us delta G equals to delta H plus T into brackets change in the change of Gibbs free energy over with time at constant pressure. So delta G here, we have been given the values for delta G and delta H. So we have these two, and we also have the value of T. So of course now here it is in degrees Celsius. You have to convert that to Kelvin. When you see capital T, you know that is in absolute temperature. If it was small t, then that is in degrees Celsius. I hope that one is established by now. So when you substitute these values now into this expression, we get minus 56.69 equals to minus 68.32 plus 298 times change in delta G with temperature at constant pressure. So we want to find this.
Excuse me, sir.
Yes.
Yes. According to your question, I've seen that calculate the value of free energy change at 30 degrees Celsius. But the absolute temperature that we've given down there, T, is equal to 273 plus 25. I think it should be 273.
Okay. Yes. Plus 30.
Yes. Plus 30.
Yeah, is that's the question, right?
Yes, that is according to the question.
Yes. It is actually. We can change this because this one is already written. At least now you have seen that that problem. We can change this one here to 25, so that we don't have to change the calculations here. Okay. Okay, so we get this expression. So from this, we can find the value for this part of the expression. So this, rearrange it, we end up with 0.0390 kilocalories. Okay. You can confirm if that is true when you calculate this. Now, again, it changes here again, huh? Because now here we have put, no, so the first one was at 25, huh? This was at, okay, the question is still remains at 30 degrees Celsius. So this one is determined at room temperature, which is 25. But now we want to find delta G, okay, at 30. So we make an assumption now that we have found the value for this change in delta G with temperature. So we are moving from 25 to 30 degrees Celsius. So now that we have found, we are assuming that the change in delta G with temperature at constant P, assuming that it remains constant over this temperature range from 25 to 30, at 30 degrees Celsius, we can write delta G is given by, so from this expression here, we have delta G, we want to find delta G at 30. So we know what delta H is. We know what T is at this point is 30 degrees Celsius plus 273, yeah? And we know the value of this change in delta G with temperature at constant P. So we put in the values here. So remember, this 303 here, you get it from when you add 273, okay? So minus 68.32 plus 303 times 0.039. So, of course, this one should have been like this. So here you get delta G being equals to minus 56.495. So notice that here the value is not so different from this one here. It was minus 56.69 kilocalories. This one is minus 56.495. So not so different, but this is within that small temperature range. There was this assumption that change in delta G with temperature at constant P remains constant. So therefore, you see these values are very close. Delta G's at the two temperatures are close enough to each other. Another example, consider the following reaction. I hope this one is clear. That one was clear, where we consider the following reaction. This is a reaction for ammonia, nitrogen and hydrogen to give us ammonia. The free energy, I'm having some background noises. I don't know what's up. Could you please mute yourselves? Otiambo, Charles. So when you consider this reaction here, the free energy changes at 25 degrees Celsius and 35 degrees Celsius are minus 33.089 and minus 28.018 kilojoules, respectively. Calculate the heat of reaction. So here you're supposed to calculate the delta H. So now we know this expression here, delta G is given by delta H plus T into change in delta G with temperature at constant P. Now, knowing, just a moment. Knowing these values for G1 and G2, we can find the this expression, the change in delta G with temperature at constant P. So this will be given by G2 minus G1 over T2 minus T1. Okay, I hope this one is clear from this expression here. So this is going to be given by 0.507 kilojoules. Now at 35 degrees Celsius, delta G is given by this. The T is, of course, 35 plus 273, that is 308 Kelvin. So here, delta G equals to delta H plus T times the change in delta G with temperature at constant P. We know the value of this already now. So if you put in the values in that expression, you remain with delta H that you can make the subject of that expression and find its value. And you can confirm that the value would be minus 184.174 kilojoules. Okay. Now I want us to consider this problem here. This problem is like we are now recapping on everything that we have learned so far. So we are going to calculate, you have 1 mole of a perfect gas. Very important to remember that. At 27 degrees Celsius, you're told that it expands isothermally and reversibly from a pressure of 10 atmosphere to a pressure of 1 atmosphere against a pressure that is gradually reduced. Calculate Q, W, and then also delta U, delta G, delta H, delta A, and delta S. Okay. Now, I want you to take the next, hopefully 10 minutes should be enough. You attempt to come up with this, see how far you can go. Of course, you have to refer back to your notes to see Q, W, and the rest of these thermodynamic quantities. So let's take 10 minutes, not 10, but 8 minutes now, so that when we come back at 9, we look at this problem and shift gears from there. Okay. I don't know if we have any. I hope we have some attempts. Now, let's see this. Since the process is carried out isothermally and reversibly from 10 atmospheres to 1 atmospheres against a pressure that is gradually reduced, the maximum work is given by this expression. Okay. So we know ln or natural log is the same as 2.303 times log to base 10. That's why we're getting this 2.303. Now notice here, we are not putting any value, any other value for n, because n equals to 1 here. So we remember the expression P1 V1 over T1 equals to P2 V2 over T2. But now, since this process is carried out isothermally, it means that T1 equals to T2. So T1 can cancel out with T2. So from this expression, we get P1 over P2 equals, this is P, equals to V2 over V1. So from this, we can change that. We can substitute the V2 or V1 with P1 over P2 so that we end up, the same expression can end up to be written as minus 2.303 RT log of P1 over P2. Okay. So now that it is in pressure, because we have the description of our process is in terms of the changes in pressure. So now that we have that, we can say, put in the values. It's going to be minus RT. So R is 8.314 joules per Kelvin per mole times, so that 27 degrees Celsius, which is 300 Kelvin, times the log of 10 over 1. So here we get the value of W being equals to minus 5,745 joules per mole. Now, when we are describing the work function, or the reason why actually we call it work function, is because delta A equals to W max. Okay, so this one is going to be, delta A is also is going to be minus 5,745 joules per mole. It's the same value as the value for W. Now, we said, I think here we said that this process is taking place isothermally. So when the process is isothermal, delta U equals to 0. Okay. Now from the first law of thermodynamics, delta U equals to Q plus W. Now if this is 0, then it means Q equals to minus W. Okay. So here Q is going to be the negative value of work. So the value of W here was minus 5,745 Here it is going to be positive 5745 joules per mole. Okay. So we have found W, we have found Q, we have found delta U. Now delta H is given in this expression. It's equals to delta U plus change in PV. Okay. So this is already, we know, is 0. And then here, we're saying PV just a second here. So delta U is 0, and change in PV is also 0. So PV here is constant at constant is constant at a constant temperature. Yeah, that's why we have this PV being equals to change in PV being equals to 0, because PV is a constant. Remember this expression that we have here. P1 at constant temperature, P1 V1 equals to P2 V2. So the change in this value PV is not changing. Yeah? So change in PV equals to 0. That's why here we have this expression being delta H is going to be equals to 0. So now, I think I have repeated myself here. Now delta G for a perfect gas at constant temperature, we're getting this from this expression. I think you can confirm this. Just refer to equation E35. Equation E35 says change of G with temperature, with pressure. At constant temperature is given by V. Okay. So from this expression, we can say that delta G at constant temperature equals to V dP. Okay. So of course, from this one, when you integrate this dg from say G1 to G2, you end up with delta G. Okay. And of course, when you're talking about from G1 to G2, you're talking about the changes in pressure from 10 atmospheres to 1 atmosphere. So here, delta G equals to the integral of VdP from 10, pressure of 10 to 1 atmosphere. This, just a second. of course, from the expression, just a second, from the expression PV equals to N RT, V is going to be given by N RT over P. Okay. So here N is 1. So here you put in the value for V, which is RT over P. It is RT over P. So it's essentially you're talking about the integral of RT over P dP from 10 to 1. So this one becomes RT ln of 1 over 10. This is the same as (2.303) RT, the log of 1 over 10. So here when you put in the values for R and T, it is 8.314 and 300 Kelvin. You get the value of delta G being equals to minus 5745 joules per mole. Okay. Delta S. Now finding the value of delta S. Delta S by definition is given by Q over T. So you already know the value of Q and we know the value of T. So when you put in those values, you get delta S being equals to 19.145 joules per Kelvin per mole. Now, we can also find the value for delta S from this expression. Now, this expression here is gotten from the expression for delta G, which is equals to delta H minus T delta S. So here, if you make delta S the subject, it's going to be equals to delta H minus delta G over T. Okay. So when you put in the values, because we have previously determined the values for delta H and delta G, you're going to get a similar value for delta S equals to 19.14 joules. Is it per Kelvin, per mole, or per mole? Just check this. Joules per Kelvin per mole. Huh? Okay. So now I think that one kind of wraps. You have a question?
Yes, sir. On this slide, allow me to get clear on this. Where are you getting 2.303? Is it a must to use that 2.303?
It's not a must. You can still use the natural log.
And will you get the same answers?
Yes, because you know natural log is the same as 2 point. I think this one we established when, I don't know, maybe I never taught you 2 or 4, but we established this. The natural log is the same as 2.303 log to base 10. So let's natural log of x, for example. is the same as 2.303 log to base 10 of x. So that's where we are getting 2.303. Okay.
Okay, thank you.
I want us to shift gear to these Maxwell relations. Now, I'm going just to give you an introduction or kind of an overview of how you arrive at these Maxwell relations. And then I'm going to refer you to a particular resource where these Maxwell relations have been comprehensively derived so that you can have a look at them. Now, do you have any question?
No, mina glasi.
So, in the derivation of mathematical relationships between different thermodynamic quantities, we shall only deal with the reversible processes. So this is the limitation that we are putting on ourselves. We are dealing with the reversible processes that involve pressure, volume work in closed systems in which there are no chemical reactions. Okay. Now, from the first law of thermodynamics, no, second law, I mean, ds equals to, excuse me, q over t. And from the first law, we said du equals to q plus w. Okay. W, we have established W to be equals to minus P dV. Okay. So if we consider that, this expression becomes du equals to Q minus P dV for the first law. Now, when you combine these two expressions, how do we combine that? Because we know from this one, we get Q equals to T ds. Okay. So putting the value for Q here, du is going to be equals to TDS minus PdV. Okay. So this is the first equation, which we are going to use in our Maxwell relations shortly. When you consider the differentials for H, G, and A, from the definitions, we get the following expression. So H is given by U plus PV. So differentiating this expression, you get dH equals to du plus PdV plus VdP. Okay. Now, this expression here, from the first law where we said du equals to Q plus W, and then we said du equals to Q minus PdV. Okay. And And then we had said that Q is the same as TDS. So du equals to TDS. Okay.
Hey, yes, morning. What's wrong?
Sema John.
Nini mbaya na connection yako lecturer?
But don't worry, it's like he has lost his connection. He'll be back shortly.
Okay.
So sorry, I had issues with my power. Lost power for some time there. Let's just go back to where we were. Sorry? So we were here. We were talking about we had already derived this one previously. Yeah? So we have said from this, of course, du plus p dv equals to TDS. So here, this is the same as TDS. So here we are saying that the expression is dH equals to TDS plus VdP. This is another important expression. Just a second. I'm trying to monitor my internet because of the power. So from this expression, A equals to U minus TS, dA equals to du. So from when you differentiate this, dA equals to du minus TdS minus SDT. Okay. This from this expression here, du minus TdS equals to, just a second, minus P dV. So this means from this expression here, we can put here, replace with minus P dV. So essentially, the expression we are ending up with is dA equals to minus SDT minus P dV. So this is another important expression. Considering this other expression for G equals to H minus TS. Now when you differentiate this, dG equals to dH minus TdS minus SDT. Okay. This we had come up with dH being equals to this du plus PdV plus VdP. That is the same as the expression for, just a second, for dH. So if you have this, now when you introduce the expression for du into this, du is the same as TdS, so du is the same as TdS minus P dV. So if we put this expression now into this one here for du, this becomes equals to TdS minus P dV plus P dV plus VdP minus TdS minus SDT. So of course, naturally you have P dV cancelling out and TdS also cancelling out. So you remain with this expression for dG minus SDT plus VdP. Okay. So here, remember we are having four expressions. This one for dG, this one for dA, the third one for dH, and the first one for du. So these four equations here, this one, just a second, we have this one where S for entropy and volume are the variables. And here we have S and P being the variables. And here we have T and V being the variables. And here we have T and P being the variables. So from these four expressions, we can come up with what we call the Maxwell relations for these thermodynamic quantities. equations are sometimes called the four fundamental equations of thermodynamics. They may be compared with the mathematical expressions for an exact differential. So you first of all, you consider the function, the particular quantity or thermodynamic quantity being a function of two variables, so that when you differentiate it, you get an expression like this. Okay? So if you're considering u being a function of x and y, differentiating this, you're going to get du dx with y constants, dx, plus du dy with x constant, dy. Okay, this is how you would write the differential for this particular function. Now, I want us to consider the internal energy. So of course, you pardon my writing here. So internal energy is given by U. So here, just remember for these four expressions, we have for internal energy, for enthalpy, for work function, and for Gibbs free energy. So you're supposed to come up with the Maxwell relations for these four expressions. So here we are starting with the internal energy, U. And we have said that U is a function of two variables, S and V. Okay. So the expression that we had in that the four expressions was du equals TdS minus PDV. Okay. So, but now here, if you come and consider that this is a function of these two, the differential for this du from our previous general expression is going to be given by du or delta U delta S with V constant ds plus delta U delta V with S constant dV. Okay. So now all these are expressions for du. If we equate the two now, so that is, you equate this to this one here, TdS minus PDV. So if you're equating these two, so notice here we have the S here and we have the S here. We have the V here and we have the V here. So essentially it's as if we are saying that this t is the same as this part of the expression. We are saying t equals to delta u delta s as constant v. And here we can also say minus p would be equals to this part of the expression. So we can also say minus p equals to du over dv at constant s. Okay. So when you consider this part here, this first one, if you differentiate this, both sides, you differentiate both sides of this expression with respect to v while keeping s constant. So this one, differentiating this and keeping s constant, this one becomes keeping s constant du ds at constant v would be equals to, so I've just swapped the sides. Just remember here we are differentiating this part here with respect to v with s constant. So this is what this expression means here, part. So here, this is going to be equals to delta t delta v with s constant. Now this part of the expression can be written, can be separated. You can write it as delta v at constant s, and then delta s at constant v of u equals to delta t over delta v at constant s. Okay. So we can also, the same way we have treated this expression for t, we can also deal the same way with this expression for minus p. Okay. So when you do that, that is, you differentiate both sides of that expression with respect with respect to S while keeping V constant. So here this becomes differentiate with respect to S while keeping V constant of this right-hand side expression is going to be du delta U over delta V as constant is the same as minus delta P over delta S keeping V constant, okay? Now, the same way that we treated this one here, this part can be separated. It can be written as d ds at constant V, and then d dv at constant S for U equals to minus dp ds at constant V. So we have this expression. This part of the expression here, the left-hand side, you can swap the differential so that it becomes d dv at constant S, and then d ds at constant V of U. So notice that this part of the expression now becomes the same as the left-hand side of this other expression we had ended up with. So it means that if these left-hand sides are the same, then the right-hand sides of these expressions would also be the same. So from there, we end up with the first Maxwell expression that equates these two, equates this one with this part of the expression. These are the right-hand sides of these two expressions. So here we end up with the first Maxwell expression, that is dt over dv at constant S equals to the right-hand side of the other expression, that is minus dp over ds minus dp over ds at constant V. So this is the first Maxwell relation. So all the other the others, remember we had four expressions. So all the others, you can also follow the same derivation, and you will end up with three other expressions or three other Maxwell relations. So they would also do that. You end up with these four Maxwell relations. This is the first one that we have derived. We derived this by considering the internal energy expression. So for the other ones, you come to these expressions here. We have dealt with this one here for du. So with these other three, you deal with them the same way that you have dealt with this one for internal energy. You will end up with these three other Maxwell relations. Now I want to refer you to a resource that you can use.
I can't hear you.
Sorry? Can't you hear me?
We can hear you.
Okay, so that maybe that has to do with whoever was saying they can't hear me. So you check their connection. So we are saying when you deal with the other three expressions, you're going to end up with these three Maxwell relations. Now I want to refer you to a resource. I found someone in the internet who has done a good job in deriving these expressions. So maybe you can write down this website, and you can visit it, and you can see how he has derived these other three expressions. So the email address is devdude.me. So this is a dot here, and then /blog / Maxwell relations. So just visit this, and you will see how he has derived this. This is an R. But you don't mistake it for a V. So it's devdude.me /blog/Maxwell relations. He describes how you can end up with all these four relations. I've only showed you how to come up with this relation here. So you can just take some time, even now after this, you can just go and have a look at these four relations. And